All right, so let's try out this problem. Sum of distances and tree. Let's have a read. There is an undirected connected tree with n nodes labeled from 0 to n minus 1. Okay, so there is a tree and it has n nodes. You are given an integer n and the array edges where edges of I equals to ai bi. It indicates that there is an edge between. Okay, so you are given an array of edges. Return an array answer of length n where answer I is the sum of the distances between the ith node in the tree and all other nodes. Okay, so for every node, we have to find the sum of its distance from all other nodes. Okay, so for example, for 0, 1 and 2 are at 1 node, 1 distance apart, 3, 4, and 5 are 2 distance apart. So 1 plus 1 plus 2 plus 2 plus 2, which is what this is. Similarly, if we solve for 5, so for 5, let's see. So for 5, how much is 0 apart? 0 is 3 apart. And sorry, 0 is 2 distance apart. 1 is 3 distance apart. 2 is 1 distance apart. 4 and 5 are 2 distance apart, right? So it's 3 plus 2, 5 plus 1, 6 plus 2, 8 plus 2, 10, which is what 10 is. So that's the question. Now, how do we solve it? So if I have to find distance for any, just basically if I have to get the answer for any of the node, I guess I can simply do a traversal from that node and then keep track of the distance and keep adding the sums of distances, right? So for 0, I do, then I keep track of distances. I can do level order, I can do depth first, whatever. So for 1 and 2, I'll add 1 and 1. For 3, 4, 5, I'll add 2 to 2. Similarly, if I start from 5, so for 2, I'll add 1. Then for 0, 3, and 4, I'll add 2. And for 1, I'll add 3. And right. So I could do this traversal with which each for each node, I can do the traversal from that node and I can solve. Now the question is, and that's the interesting question, which is, um, what's the total time complexity? And the total time complexity, so for one node, you're traversing all n nodes. For n nodes, for each of node, you travel n nodes again. So the total time complexity becomes n squared. Now the question is, can I make it better? Can I do better than n squared? So let's say I solve the problem for 0, right? So I get the answer for 0. I can do it in O of n time. Now, do I really need to, can like, so the question is, once I found the answer for 0, can I find the answer for 1 or 2, which are directly linked to 0, right? So when I find answer for 0, that means I consider the tree to be rooted at 0. And based on that information, can I do, there is some relationship. You can imagine duplicate work like for, like if I know the answer for 0, I already sort of would have calculated all of this, right? Because it's a subtree of this. Similarly, I would already calculate this. So let's try and build some relationship and see if we can find some relationship. So switching to a whiteboard, and let's take some random tree. So let's say a tree is 1, 2, 3, 4, 5, 6, I don't know, 7, and then 8, 9, some random, completely random tree. Now, what we do is we consider the tree rooted at 1. We could consider the tree rooted anywhere, but let's say we do consider the tree rooted at 1 and we solve for 1, right? We solve for 1. Now, let's, can with 1 can I solve for 2 and 3? So let's try and solve for, let's look at this 1 and 2 relationship, right? Let's divide the tree into two parts. One is this and the other is this part. Let's call it set A and let's call this set B. And now let's see if we can find some relationship. So uh, let's define few things, huh? So we are considering the tree at, we are considering the tree rooted at 1. Okay, and let's say we are calculating total sum. So let's call it sum. So what is the sum for 2? So let's say if we calculate the sum for 2 in this set A only. So sum of 2 in set A only. Then, okay, let's say we calculate that somehow. And then the difference between set A and set B is all the nodes in set B are one extra distance apart from 2 than they are from 1, right? And similarly, all the nodes in set A are one extra distance apart from 1 than they are from 2. So if I have to solve, like if I want to get the sum of from 2 to 3, like distance from 2 to 3 is distance from 1 to 3 plus 1, right? So essentially what I mean is essentially summation of for each node, its distance from 1 plus 1, right? And this is for all nodes in B. So essentially what this becomes is sum of 2 in A. If you think about what this represents, is essentially sum of 1 in B and plus this is the number of nodes in B, right? So this is what you get for sum of 2. You can do the same thing and you can say sum of 1 would be sum of 1 in B plus, so sum of 1 in B is this, and then sum of 2 in A plus all the nodes in A, right? This is what you get from A, this is what you get from B. Now you can clearly see there now if you could subtract these two, you just essentially get sum of 2 minus sum of 1 equals to number of nodes in B minus number of nodes in A. And what we talked about is let's imagine we solve the problem for 1. So we already have this, right? And also, uh, let's say n is the total nodes, then you can also write nb as n minus na. So this essentially becomes n minus 2 times na, right? So essentially what you get is sum of 2 equals to sum of 1 plus n minus 2 times count of 2, right? And count of 2 is the number of nodes in the subtree rooted at 2 when you are considering the entire tree rooted at 1, right? And which is what we are considering. We are considering the entire tree rooted at 1. And so when you look at the subtree rooted at 2, how many nodes are there? That is what we are considering, right? And similarly, if you solve for this, then you can get sum of 4. So similarly, once you get 2, you can then get the same for 4. So sum of 4 equals to, again, sum of 2. Now you're considering this 2 to 4 edge plus n minus 2 times count of 4, right? That's a general idea. Similarly, for 3, you would consider this 1 and 3 edge, and sum of 3 equals to sum of 1 plus n minus 2 times count of 3. That's a general idea. Now, how do you? So sum of 1 is something that we'll solve. So we need two things, right? And then we can recursively go down from 1 to 2 to 3, but we need two things. In the first stage we need to solve for this one, and also we need to get these counts for each and every one, right? So let's try and do that. So let's consider, let's say, essentially we have to get two things sorted, right? Uh, One is we have to find this total sum. Okay, let's write it again. So we have to solve this total sum, and we have to also find this count. So we do, let's say, whatever it's called, process or traverse, and we pass the node, initial node, which is whatever 0, and its distance is also 0. So we define some node, and we define some distance that this guy is from the root node, right? And so what begin with this, what we do is okay, so we know we are trying to solve for total sum of 0. So total sum of 0, this is index and this is distance. Total sum of 0 uh, plus equals to distance, right? So this specific node is a distance d away from that. And then you also want to process all the children. So you do traverse each, okay, for each child, traverse child with distance plus 1, and then you can get count of index plus equals to count of that child, right? And something like around that figure. But okay, that's just code. But the general idea is this that we just talked about. That if we solve for 1 and we get the count of all the subtrees, then we can just build the entire thing. Let's come to code to see if it makes sense at all. So, so we want to solve for two things. One is, let's we want to we assume consider tree rooted at 0, right? And you're getting two things. One is the total sum that you want to return, size is n, and we also want to get the count, number of nodes, right? So count new int of n, and eventually we just want to populate total sum, so return total sum. So first what we do is we do populate, count, and solve for root, right? That's the first thing we want to do. And there we pass 0, and there we pass, okay, let's first build the tree in a adjacency list format. So you have your list of integer adjacency list equals to, there are n nodes, so 0. Let's create an empty list. And then go through the each and every edge. So for each edge and edges, let's in the adjacency list of edge of 0, we add edge of 1. In the adjacency list of edge of 1, you add edge of 0. This is the adjacency list representation, and we'll pass this adjacency list representation to this guy. And also let's pass the distance, call it distance. So what I mean by distance is I want to keep, I want to solve for root, right? So I want to keep track of distance from root. So maybe when I write the function definition, maybe more clear. So populate, count, and solve for root. What I want to do is this is a bidirectional graph too, so I might also want to pass in previous or something. So it's called -1. So basically, if I go from 0 to 2, I don't want to go back to 0. So I want to know where I came from, which is what this would be. So um, I'll call it node. I'll call it distance uh, from root. I'll call it uh, adjacency list, and then I call it int previous or parent, right? So that's the idea. Now what I want to do is firstly I want to also populate his total sum. So let's pass these two arrays as well. Integer array total sum and integer array count. So total sum as well as count. I want to populate total sum of 0 and I want to populate counts, right? So first thing is uh, total sum of 0 plus equals to distance. This guy is root, so you add the distance of this guy from root, and for each of its child, so for each int child in adjacency list of node, so for each child, obviously you don't want to go back to the parent. So if uh, like this is the case you want to avoid, then what you want to do is this: you want to call again the same thing. So you call it for each child. Now distance from root will increase by 1, and you pass in the adjacency list. Now the parent will be this node, and you pass in your total sum, you pass in your count. Okay, and once you solve a specific child, another thing that you can do is so count the number of nodes in the subtree. One thing I can also do is at least this guy is there, so count of I at least is 1, right? This guy, I add myself in the subtree, and then I'll add all the nodes in the subtree of each of my child. So count of what is this I node? So count of node uh, count of node plus equals to count of my child, right? So this is the one that is populating the count and solving for root. Now once I do this, I have total sum of 0, and I have the once if I consider the subtree rooted at 0, then I have the uh, number of nodes in the subtree for each and every node. And this you can see will happen in O of n. And the equation that we came up with, let me go back to the whiteboard once again. So this equation that we came up with, oops, where sum of, let me de-highlight it, right? So essentially, this is what we will use and do another traversal and populate the, we already have sum of 1, or like the sum of the root, whatever, and based on that, we'll populate the total sums for all others. So this is the equation: sum of a child equals to sum of parent plus n minus 2 times count of the child, right? So let's go back to the problem. So now once we do this, we'll do populate total sums for all, right? And now what do we want to pass in? Okay, so I want to solve starting. I want to. Okay, so start from 0. Populate. I definitely want to pass in this. I want to pass in a previous guy. I want to pass in adjacency list. I want to pass in total sum. I want to pass in count. Okay, so let's do this. Void populate total sum for all. Node, its parent, and then the adjacency list and the total sum and count array. And you're starting obviously from 0. So now, so all I have to do is this. I already know my value, so I have to populate all my children's values. So for each uh, child in this, for each of this guy, again, we don't want to keep on an infinite loop and go back and forth and back and forth. So if child equals to parent, you want to ignore that condition because of the bidirectional nature of the graph. And now your total sum of each child equals to total sum of this node. What was the condition? Plus n was length, so anything you can take. Total sum dot length, these total nodes, minus 2 times the count of child, right? So you do this for each and every child. So I do this for this child, and once I do this for this child, I would want to populate for its child as well, right? Recursively. So, and then we call for this. So you go child, you go now parent will become this, adjacency list, total sum, and count. And I guess that will just populate it, right? That is all. And this loop again will run in overfan, this loop again will run overfan, and the space complexity is overfan. Uh, yeah, let's run code and fix issues. Okay, it works. Let's run for example test cases. Okay, submit.